What's up, guys? Today we're going to be talking about inverses of functions. Now, hopefully you've already watched the video on function composition and you understand how function notation works. So functions that are inverses, what does that mean? Well, the inverse of a function undoes the other function. So take, for example, the function f of x equals x plus 1. Now let's make sure we understand what we're saying here. F of x equals x plus 1 says if I plug a number in for x, I'm going to add 1 to that number. You could even make a table of values. What would happen if we plug something into this function? Let's just take a few numbers, 0, 1, 2, and 3. Suppose I plug 0 in for x. Y would be what you get out of the function. In other words, f of x. F of x and y are interchangeable, okay? So if I plug a 0 in for x, what do I get? Well, I'm going to add 1 to that, so I'm going to get 1. What if I plug a 1 in? Well, 1 plus 1 is 2, okay? Similarly, if you plug in a 2, you get a 3. If I plug in 3, I'm going to get 4, okay? So this is a function that simply takes an input and gives you back an input, which is 1 more than whatever you plugged in. Well, what would be the inverse of that function? What kind of function would undo what that function did? That function we call the inverse, and we note the inverse like this. We raise the function to the -1 power, and that simply is a notation saying it's the inverse of the function f. It's not to be confused with the exponent rules we learned earlier. This is a notation purely for functions saying that it is the inverse of the function, okay? The inverse f of x, in this case, would be x minus 1. So what this is saying is you're going to take something, you're going to plug it in, and then subtract 1 from that. It's going to be 1 smaller. So if you made a table for the inverse f of x, it would look like this. Again, this would be the inverse f of x. So if we were to plug in some numbers, and just instead of plugging in any old numbers, let's suppose we plugged in what we got out of the other function. So we plugged in a 0, and we got out a 1. Well, over here, what if we plugged in a 1? What would we get out? A 0. Notice that they've switched places. You plug in a 0, you get a 1. If we take that 1 and plug it into the inverse function, we get back the 0 we started with. What if we plugged in a 2, or a 3, or a 4? If you plug in a 2, you're going to subtract 1 and get 1. If you plug in a 3, you'll get 2. And if you plug in a 4, you're going to get 3. Notice the x and y columns have switched on these two functions. So that's one way of thinking about the inverse. If you have x, which is an input, and y, which is the output, the inverse will have those switched. Now, I have a picture of a function and its inverse here. And as you can see, this inverse is a little more complicated than the ones we've seen so far. And we are going to talk about how to find these inverses. But before we did that, I want to show another way to look at a function and its inverse, and that is looking at the graph. So we talked about how if you were to make a table for a function, then its inverse would have the coordinate pairs, or the x and y, flipped. And as you see here, the point 0, 1 and the point 1, 3, that blue line represents f of x. And you can see that these are points in the function. If I plug a 0 into x, 2 times 0 plus 1 gives me 1. If I plug a 1 into x, 2 times 1 plus 1 gives me 3. So these are points that you get. In other words, they're also pairs of coordinate pairs from the table we made before. Well, if you look at the inverse, it's in red or in orange. I'm not sure what that is on your screen. But these two functions, the function and its inverse, they have a pattern when you look at the dotted line, which is y equals x. Now, y equals x, which you could also say f of x equals x, this function is a line where the x and y coordinates are the same. So it passes through 0, 0, and it goes to 1, 1, 2, 2, 3, 3, 4, 4, and so on. It's just a 45-degree angle passing through the origin. And as it turns out, any inverse function, any function and its inverse, will be in this pattern around this dotted line. And that pattern is the reflection across that dotted line. And again, that's because, as we saw on the table, the x and y coordinates are flipped. 0, 1 becomes 1, 0, 1, 3 becomes 3, 1. all functions and their inverses are going to have this same pattern, which is kind of neat because if you know what the graph looks like for a function, you can draw its inverse very simply by flipping the coordinates of every point. It actually makes graphing inverses very simple to do. All right, so let's go back to inverses and how do we find the inverse of a function? So let's start with a new function. And this one's going to be a little more complicated, one that's not quite as obvious. We know the opposite of doubling is cutting in half. The opposite of tripling would be taking 1/3. The opposite of adding 5 would be subtracting 5. What happens when you do multiple things at the same time? Can you just say if f of x equals 2x plus 3, well, that's adding 3 and you're multiplying by 2. So do you think the inverse f of x would simply be 1/2 x minus 3? You're doing the opposite there and you're doing the opposite there, so you might think so. But it's actually not. In fact, you can very easily check this. If you plug anything in for x, like say I plug in a 0, I'm going to get plus 3. If I plug in 3 here, I'm going to get, let's see, 1/2 minus 3, which is negative 1/2. So clearly these are not opposites. So it's got to be more complicated than that. This is not the inverse. So how can we find the inverse for 2x plus 3? Here's the process that I like to use, and there's probably different ways to do it, but this is the way I do it. The first thing I do is, because I'm going to be doing some algebra, I want to make it easier to write than just f of x. So I'm going to use y. I'm going to change the f of x to y just temporarily, and we'll come back to it. So all I've done is just replace the f of x with a y. It basically means the same thing. Now, usually when I work downwards like this, I'm doing algebra steps, and each equation would be equivalent to the previous equation. But what I'm about to do is going to change the equation. It will no longer be equivalent to what it was. So this is the function f of x. I'm going to draw a line here, and anything below this line is going to be the inverse. It's actually that easy. In one step, I'm going to have the inverse. And that step is simply to, as we said before, switch the x and the y. If I say x equals 2y plus 3, that is the inverse. In fact, I'm going to do some more work, and everything below this is the inverse. We no longer are working with the original function. The only problem is we don't usually want to write a function this way. We want to get that y first, so I can go back to calling it f inverse x. So how do we do that? Well, the same way you always solve for a variable. We want to get y by itself. So what this means is we're going to have to undo everything on that side of the equation until the y is by itself. So going in the reverse order of operations, we're going to subtract the 3. Then we're going to have to divide by 2. Okay. Now, we can flip this around if we want, and we could actually just say y equals x minus 3 over 2. But I don't really want to leave it as just one big fraction like this. And there's a few reasons for that. But since this is a linear equation, I'd like to write it in slope-intercept form. So to do that, I'm going to split the fraction into two fractions. And I'm going to say x over 2, and I'm going to have negative 3 over 2. I'm just going to split them apart, because you can do that. So I'm going to say x over 2 minus 3 over 2. And you would agree that's the same, right? In fact, you could even go a step further and really make it look like slope-intercept form. Instead of saying x over 2, I'm going to say 1/2 x minus 3 over 2. Now, I'm not always going to write this many steps out, but I want you to see how I went from this to this, which, of course, this is slope-intercept form. Y equals mx plus b. This would be your slope, and this would be your y-intercept. So for the last step, we're going to say f negative 1, so the inverse f of x equals 1/2 x minus 3/2. This is the inverse of f of x, which was 2x plus 3. So that was a lot of work. Not too hard, but I know it looked like a lot, and I think when you practice it, you'll see that it's really not too hard. But how do we know that we got the right answer? It looks kind of weird. It doesn't look very obviously like the inverse, at least not until you do it a few times. How can we check? How can we verify that two functions are inverses? If I say that these are inverses, how can I prove it? If someone asks you to verify that two functions are inverses, this takes us back to what we did in the last video, which is function composition. If we do the composition of a function and its inverse, we should get back what we started with. Because remember, when we do composition, we're plugging something into a function and taking that output and plugging it into the other function. Well, we already said if we plug something into f, then take that output and plug it into the inverse of f, we should get back what we started with. Well, rather than plugging in a specific number, because sometimes one certain number may come out the same, we want to check all numbers. And so to do that, we're actually going to plug in x, meaning we're going to compose the functions themselves rather than plugging in a number. So I'm going to check f of the inverse f of x. I'm going to plug the inverse f of x into the function f of x. So I'm going to take f of x, leave some space, and plug in the inverse. And then we're just going to work this out using the order of operations. 2 times 1/2 gives me 1, so that's just x. And then 2 times -3/2, notice the 2 here will cancel with the 2 on the bottom and give me -3. Now this is still in parentheses, and I have a +3. And now for the final step, I'm going to combine these like terms. The -3 and +3 cancels out, and I get just x. This is what you want to see if the functions are inverses. If this doesn't happen, they're not inverses. Why? Well, let's think about that for a minute. I took the x and I plugged it in. In this case, x went into the inverse here, and then I took what came out of that and plugged it in to f of x. So by plugging x into a composition of two functions, you're essentially plugging it into one, taking that output and plugging it into the other. And since I originally plugged in an x and I got out an x, that means they canceled each other out and I got out what I put in. They undid each other. Now we always need to check and make sure it works both ways. It usually does, but just to be sure, we're going to check it the other way too. So we're going to do the inverse f of x. So I take the inverse f of x, which is 1/2, leave space for x, minus 3/2, and in here I'm going to plug the other function, f of x. And again, working this out, 1/2 times 2, just 1. So again, I have x. Now I've got 1/2 times 3, and I'm just going to leave this as 3/2. And finally, I'm going to combine these, and as you see, they cancel out, leaving me with just x. So in both cases, I got what I plugged in. It went through both functions, and they undid what the other one did. So whatever went in is what came out at the end, meaning the two functions are inverses. That's how you verify that functions are inverses. And this wraps up the videos on inverses of functions.